Hey, welcome to the Unit 4 guided notes video. Today we're going to focus on the first half of the Unit 4 guided notes, talking about solubility a little bit, and then talking about chemical reactions. For these last couple of pages, there's actually going to be a separate video poster for those. Those are all on redox reactions, which those examples are really long. And I think the video should stand by itself, mainly so if you want to go back and watch it later, it's a lot easier to find. So a couple really important topics today. Um, let's go ahead and get started. So Unit 4 is about types of chemical reactions. These are things like single replacement, double replacement, synthesis, things you've heard about a little bit last year, but we're also adding on some new ones. We're adding on redox reactions is the big one. We're adding on acid-base reactions with a lot more depth than we talked about last year. And then the second part of what we're doing today in this video is solution stoichiometry. So solution stoichiometry, the word stoichiometry just means when you have a chemical reaction changing between the quantities in that reaction. How much products, how much reactant changing between those values. And the word solution just means you're going to be looking at solutions for this today. Things that are dissolved in water or other solvents, but really just water. How do you do the math between those, between ions, between acids and bases and other aqueous sort of solutions? We've done a lot of stoichiometry this year. It's really important to get the math down. The concepts are going to be the same as what we did a little bit earlier, but there's just a couple of new things we need to learn with solutions. Okay. So we're going to talk a little bit about water. A lot of this is review, stuff we know. A couple of keys. Water is one of the most important substances on Earth, for sure. It can dissolve many other substances. Anytime we make a solution in class, if we make a solution in the lab, we always use water as the solvent. It's a really good basis. It dissolves a lot of things, and it has really good properties that help it do that. Main thing being that it's polar, which we've talked about. It's made of two hydrogen bonds. Those hydrogens bonded to the oxygens creates a very highly electronegative bond difference between the two. It means you have a very strong partial positive charge on both your hydrogens, which is useful for attracting negative charges. And you have a very strong negative partial charge on the oxygen atom, which makes it really good at attracting and dissolving positive things. H2O has this bent shape that we talked about with Vesper shapes. There's 104.5 degrees between the hydrogens. And then last thing here, hydrogen, H2O is a polar molecule because the oxygen atom has a high attraction for electrons. Okay. A little bit what I was talking about on the last slide, hydration. As ionic solids dissolve in water, like salts, NaCl, KCl, anything like that, ionic solids made of a positive and a negative end. They break up when they go in water into their positives and negatives. The positive ends of the water attract the negative ends, the anions of the salt, and then the negative ends of the water, the oxygen atom is able to attract the cations. Water is excellent at dissolving ionic compounds because it has that positive and negative end from the hydrogen bonds. Talking about solubility is basically what dissolves inside what. Like salt, for example, is highly soluble in water, but it might not be soluble in other solvents. Things like oils and stuff, salt might not dissolve as well in those. But other things like sugar is, I would say, like slightly soluble in water. If you have like a cold thing of water and you add some sugar into it, it doesn't dissolve very well. But if you like use a hot cup of coffee or something like that, then the sugar is going to dissolve really easily. Okay. We've talked about this, like dissolves like. Polar things dissolve other polar things. Non-polar things dissolve other non-polar things. Okay. But water is able to dissolve non-polar things as well, not strictly ionic things. Look at ethanol as an example. So its formula, C2H5OH. It's written like that for a reason, where it has 5 of the H's written together, but one of the H's written at the end. It's trying to give you a hint about the structure of that molecule. So I'm just going to quickly draw that Lewis structure. So we have C2H5OH. Okay. So the C's are going to kind of go in the middle. I'm just going to do 2 C's like that. And then I have 5 just regular H's. And I'm just going to start going around satisfying the octet rule. So this carbon has 4 bonds now, so I can't add any more. It's good. But it's 3 of my hydrogens. I'm going to put 2 of my regular hydrogens over here. But this carbon has 3 bonds now. It can take 1 more. So it's going to bond to this O and H. Okay, O and H. It's written like this just to help you draw the structure. C2H5OH. The O and H are attracted to each other. This O is bonded to an H. This is a hydrogen bond. Okay, so this is you're gonna have a partial negative on this oxygen, a partial positive on the hydrogen. So if this interacts with a water molecule, it'll actually be really good at dissolving this because of the polar bond. So even though this entire thing is a covalent compound, it still dissolves well in water. We're going to talk today about why some things dissolve in water, why other things don't. Some ionic things do, some of them don't. Some covalent things do, some of them don't. Thus, ionic and polar substances dissolve well in water, but non-polar substances really don't. So anything that's ionic, so any salt, will usually dissolve in water. We're going to talk about those exact rules a little bit later, but polar things generally will dissolve in water as well. All right, so the nature of aqueous solutions. A solution is a homogeneous mixture made up of a solute. Solvents, you've probably learned about this every year since like 6th grade, but a solute is whatever is being dissolved. So it's just usually like a solid that you start with, and you're going to take just a little bit of it and dissolve it in your liquid. And then the solvent is that liquid that's doing the dissolving. Now, a solute doesn't always have to be a solid. It can be another liquid being dissolved, but it's easiest to think about it that way. The solvent is whatever's doing the dissolving, usually water for our cases, but you can have other solvents. And then aqueous solution is just talking about solutions which water is the solvent, things that are dissolved in water. So if I tell you have an aqueous solution of salt, that just means salt water, salt that's been dissolved in water. Another kind of interesting word here is electrolytes. We talk about this a lot with like our diets, drinking a Gatorade after you work out for the electrolytes. But electrolytes really just means salt, or things that like conduct electricity, which is usually salts for our body. Electrical conductivity is the ability of a solution to conduct electricity. We have things like strong electrolytes, which means they conduct electricity very well. So if you had like a light bulb hooked up to like a strong electrolyte, it would shine very brightly. A weak electrolyte conducts only a small amount of current, so this might be a partially soluble salt or something like that, where it does conduct electricity but doesn't do it very efficiently. But then you have non-electrolytes where no current will flow. Things that are not so soluble, that don't conduct electricity. Here's some examples of the couple different versions of strong electrolytes. So the 3 different classes here. We have soluble salts, things like NaCl that fully dissolve in water, are going to be strong electrolytes. The positive and negative ends are good at conducting electricity. Having those full positive and negative charges just conduct them well. And then also the strong acids and strong bases. When these are dissolved in water, acids will give up their H plus ions. We're going to talk more about acids very soon actually, but when you have an acid like hydrochloric acid, HCl here, when you put it in water, it's going to break apart into 2 parts. It's going to lose the H plus, and then it's going to lose whatever else is with it. So in this case, the Cl minus. And that creates some ions as well, some full positive and negative charges that are good at conducting electricity. And then strong bases are pretty much the same, but just the base version. NaOH is the most common strong base we use, so that's going to split apart into its 2 parts. It's going to make an OH minus, an hydroxide ion, and then a sodium plus. And those full charges are what help conduct electricity. Remember, electricity is just the movement of electrons. So electrons have a negative charge. They need things with positive charges to attract to move through a solution. And all of these produce full positive charges to attract them. Here are some weak electrolytes, things that dissolve a little, but the majority of the solution doesn't fully dissolve. So this would be like something you add to water, and like part of it's going to dissolve, but like it doesn't fully dissolve. So imagine you take like a thing of sugar and you just pour ice cold water on it. Some of that sugar is going to dissolve. If you tasted the water, it'd be a little bit sweet, but you'd have a big clump still at the bottom. That's what I want you to think about when you think of something slightly soluble. Is like some of it will dissolve, but you need to stir it for like a long time, or it won't ever fully dissolve. So here's some slightly soluble salts. Things like BaF2, barium fluoride, is an example of something that's not going to fully dissolve. And then the weak acids and weak bases. We're going to learn a lot more about weak acids and weak bases as well. These are things that act like strong acids. So weak acids, if you look back here at HCl, it splits apart into H plus and Cl when you put it in water. But a strong acid will do this nearly 100% of the time. Almost 100% of my HCl molecules will split apart this way. But with a weak acid, that's not the case. It kind of is like a slightly soluble salt, where only some of those acids are going to break apart into their compounds. And same for weak bases. Only some of them are going to split apart into their hydroxide ions. Then we have non-electrolytes. These are things that can dissolve in water, but they don't produce any ions because they don't have positive and negative charges. So here's our ethanol example again. This is soluble in water. It's dispersed in water, but doesn't break apart. It just stays kind of as it is, and water is just able to like kind of dissolve it, but it doesn't split into other little things. Things like sugar would do the same thing. When you dissolve sugar in water, it's not splitting into the carbon and hydrogens. It's staying as sugar, which is why we still taste sugar. Okay? All molecular substances will act this way. Now, we're going to review quickly because it's really important kind of going forward. We've talked about this a lot in the lab and in the classroom. Molarity, and then we're actually going to do dilution after this. But real quick, molarity, which we know, is just how concentrated something is. It's the moles of solute per volume of the solution in liters. If you write down that formula real quick, molarity is moles of whatever you have divided by liters. Let's just go ahead and do an example of it real quick, just to make sure we have it. So, okay. 500 grams of potassium phosphate. No idea what that is, but let's just go with it. It's dissolved in enough water to make 1.5 liters of solution. What's the molarity of it? Molarity equals my moles of solvent. So I need moles. The thing that's being dissolved is going to be this compound here, potassium phosphate. Now the problem was mean. It didn't give you the chemical formula, so we have to kind of write that ourselves. So potassium is K. Phosphate is one of our polyatomic ions we should know. It's PO4, has a charge of 3 minus. Now, if I flip over to my periodic table, K, potassium, is in the first column. It's an alkali metal, so its charge is 1 plus. So I'm also going to write its charge here. Now, this is an ionic compound because they both have charges here. But when these two things combine, we need to remember not to just write the two things together. KPO4. Like, that's not the actual formula here because we need these charges to cancel out. We can't have a leftover charge. So I have a 3 negative charge here. So I need this to be 3 positive to cancel. So I'm going to make 3 Ks so that this is 3 plus instead. And now if I add these two things together, I have K3PO4, like that. The 3 plus and 3 minus cancel. Okay. So I have my moles of this compound, K3PO4, potassium phosphate. It's dissolved in enough water to make 1.5 liters of solution. This might sound slightly strange, saying it this way, but basically it's saying you have 1.5 liters of solution. But the way it's phrasing it like this, it's actually just being a little bit more exact. If you think about it, if this solution, this 500 grams of solid, is going to take up a little bit of the space in my liquid. So I'm not actually adding 1.5 full liters of water. I'm adding enough water to make the full solution 1.5 liters. I might only have to add 1.4 liters of water. But basically, this is just trying to simplify the math and make it look more correct. It's just saying you have 1.5 liters of the whole solution overall. I need to find moles of K3PO4, but it gave me grams in the problem. So I'm going to have to do a little conversion. 500 grams of K3PO4. Convert it to moles, so grams on bottom, moles on top. How many grams are in a mole? I need my periodic table for that. So I'm going to go to my periodic table. K weighs 39, and there are 3 of them. And then I have PO4, so I have phosphorus, which is 31, and O4. So just on my paper here, I just jotted them all down. multiply these across to get, because I have 3 potassiums, I have 4 oxygens, and then just add up my final answer. When I do that, I get like 212 grams per mole. That's what I'm going to plug into my expression up here. There's 212 grams in every 1 mole. Do my math across, and then I'm going to do my 500 times 1 divided by 212. I get a number 2.358. I'm just going to write out those 4 digits. Okay. Well, that's how many moles I have, so now I'm just going to take that and plug it back into my equation here. 2.358 divided by 1.5. That'll be my final answer, and I just get like 1.57. Just going to round my final answer to 3 digits there. My units for molarity, it's just moles divided by liters. Okay. Hopefully that's just review, but that's really an important part of the exam, is being able to do that. I know we haven't talked about it specifically in a while. Okay, so it says, realize that the solution concentration is given in terms of the form of the solute before it dissolves. What that means, if I go back to my answer here, this molarity is the molarity of my K3PO4 before it dissolves. When this dissolves, it's going to split apart into multiple different things. But this is the molarity of just that entire compound before, but not necessarily the molarity of my potassium ion in my solution. So let's talk about that's going to look like. All right, so here I have a 0.25 molar calcium chloride solution. Calcium chloride is CaCl2, made of 1 calcium, made of 2 chlorines. So the solution of the calcium chloride is 0.25 molar. Okay, but when this dissolves, this is going to split apart into its ions. It's going to split into 1 calcium, which has a 2+ charge, and then 2 chlorines, which each have a minus charge. Because you make 2 chlorines from every 1 thing that's dissolved, the molarity of the chlorine ion is actually double, because you make 2 of them every time 1 of these dissolves. Okay? So that's kind of like a mole ratio between these 2 things. I have CaCl2 splitting apart, making 2 chlorines. So 2 chlorines are coming from just 1 of my calcium chlorides, so it has double the molarity. So if I go back to my other example here, this is the molarity of my K3PO4. But if I put this in water, it'll split into 3 K pluses, because there's 3 here, and then 1 PO4 3 minus. The molarity of my PO4 3 minus, because there's only 1 of them being made, is equal to this 1.57 molar. Because 1 of these makes 1 of these. But I make 3 times as many K pluses. So its actual concentration when it's dissolved, it's going to be 3 times 1.57. It's like 4.6 something, right? It's actually going to be 3 times as much potassium in there as there is phosphate. Calculate the concentration of Cl- ions if 0.7 moles of zinc chloride are dissolved into 1.75 liters of solution. So it's important to know what concentration they're asking for. Are they asking for the concentration of the zinc chloride, the full ZnCl2? Not in this problem. They're just, I want to know about the Cl- ions. So I'm going to pull up. We have a little hints down here. When ZnCl2 dissolves, it makes 1 zinc and 2 Cl minuses. So that means whatever my molarity of zinc chloride is, the molarity of chlorine ion is going to be double it. Okay. So let's say I have 0.70 moles of ZnCl2. Okay. Well, I can just find out how many moles of Cl that makes. The easy way to do it is just to kind of realize that it makes 2 chlorines and times it by 2 and just get like 1.4 Cl minuses. but it might make more sense to work out the math. So I could just do a mole to mole ratio here. So I have moles of ZnCl2 on bottom, and I want to find out how many moles of Cl minus I have. Well, if I look at my equation here, my balanced equation, ZnCl2 and there's just one of them, so I'll just put a 1 here, makes 2 chlorines, so I'll put a 2 up here, and then just solve. My units cancel, I'm left with just moles of chlorine, go across, 1.40 moles of chlorine. So if you could just kind of reason out the answer, that's fine, but here's how you would show the work for it, just do a mole to mole ratio. What I did was just turn my moles of ZnCl2, which I don't need for my problem, into my moles of chlorine, which is what I need because I'm looking for molarity of Cl minus. So that's going to equal moles of Cl minus over the volume. My moles of Cl minus are 1.40. My volume is 1.75. Do that math, and that comes out to about 0.8 moles per liter. So that's the molarity of my chlorine ion. Okay? The molarity of my zinc chloride, if I calculated that, it's only going to be half. This one will only be 0.4 moles per liter. And same with the zinc, 0.4 moles per liter. But the chlorine, because of this 2 here, I make 2 in every reaction, it's going to be double, 0.8. All right, so we have a concept check here. Which of the following solutions contain the greatest number of ions? So greatest number of ions is going to be the greatest number of moles of ions. Here I have NaCl, CaCl2, FeCl3, sucrose. Okay, so I'm looking at all these different solutions. I have different amounts of each one, and I have different molarities, and I have different compounds. So first one I notice is D, is sucrose. Sucrose isn't going to dissolve. Sucrose just means sugar. So it's C6H12O6. It's not going to separate at all. So I'm going to eliminate D right off the bat. It's not going to turn into anything. It doesn't have a positive or negative charge. But all of these other ones turn into multiple things. NaCl will make 2 ions. It'll make 1 Na, 1 Cl. CaCl2 will make 3 ions. It'll make 1 calcium, 2 chlorines. And then FeCl3 will make 4 total ions, 1 positive charge, and then 3 chlorines. So we're going to keep that in mind. I'm going to calculate how many moles are in A, B, and C. And then the first one we're going to multiply by 2, because you have 1 Na and 1 Cl. And then multiply the part B by, or answer choice B by 3, because that's going to make 3 ions. I'm going to multiply answer choice C by 4, because you're going to have 4 ions. So if I real quick, okay, so I had, just going to write down what I had here. I had 400 mLs of 0.1 molar NaCl. Okay, that's the first one. Let's just find out how many moles that is. Remember, molarity is moles per liter. Okay. So my molarity is 0.1 equals my moles over liters. 400 milliliters is 0.4 liters. So if I do all this out, I have 0.04 moles of NaCl. So that's how much I have, but I want to know how many ions it's going to make. NaCl splits into Na plus and Cl minus, 2 total ions. So I'll have 0.04 of this plus 0.04 of this equals 0.08 moles total. And that's kind of what we're doing here with the problem. So this is how many total ions I would have in this answer. To do the other ones real quick, my CaCl2, I have 0.1 moles. And I have 300 milliliters, so I'm going to make it 0.3. Multiply it across, 0.03 moles of CaCl2. Okay, well this is going to split into Ca2 plus and 2 Cl minuses, 3 total ions. So if I times this by 3, I have 0.09 moles of total ions in this one. Right? 0.03 calciums and then 0.06 chlorines. And then my last one here, I'm going to try to just squeeze it here, 0.1 molar FeCl3, and I have 200 milliliters of it. So I'm going to multiply this across. It's 0.02 moles of FeCl3. Well, this is made of 4 total ions, so I'm going to multiply by 4. This one's also 0.08. The highest one is my 0.09. These two are tied. My highest one's 0.09 is the calcium chloride. So if I go back to my answer, that's going to be answer choice B, has the greatest number of ions. Okay. A and C would be tied for second, and then D would be last because it doesn't make any ions. All right, a little bit of terminology here. We've talked about this a lot before. Standard solution. A standard solution is just any solution where you know its concentration. So the other day in the lab, we made a bunch of dilutions of solutions, but they're called standard solutions because we knew their concentrations. I had you guys measure them out on a scale and then like add water to it so that you knew its exact concentration. So anything that's called standard is just has a standard concentration. A stock solution is usually a very highly concentrated solution of something, and you can make more diluted solutions from it. So if I go to the lab and I make a 12 molar solution of something, you could take just a little bit of that liquid and add extra water to make some weaker versions for your own use. And then a dilution or diluting something, is the process of adding water to a stock solution to attain a desired concentration. So if I have a 12 molar stock solution of hydrochloric acid that's incredibly potent, you probably don't want to work with that. So you might add in a little bit of extra water to just a small amount of my solution to make like a 1 molar solution, which might be more usable for whatever you're working with. And then also dilutions we've talked about before. There's a formula to calculate how to dilute something. M1V1 equals M2V2. Okay? Basically, if you think about it, they've rearranged the molarity formula here. And basically all it's saying is the moles of solutes before you dilute something, so the moles you start with, molarity times volume, equals the moles of your solute after, your new molarity times your new volume. When you make a dilution, the moles of whatever you have stays constant. So let's just quickly do an example of this. Some paper. What volume of 16 molar sulfuric acid? So that's 16 molar is my stock solution, but it's also a standard solution because I know its concentration. Okay, that's going to be my molarity I start with. I'm going to choose to put all my stock solution stuff on the left here. That's what I normally would do. And then my dilution information will go here on the right. My stock solution of sulfuric acid is 16 molar. What volume of that must be added? So I don't know that yet. That's my V1. That's unknown. To prepare 1.5 liters of a new solution, 0.1 molar H2SO4, which is just sulfuric acid. So my 0.1 molar is how strong I want it to be, and I need 1.5 liters of it to work with. So I'm going to solve for V1. Basically what that's saying is, how much of my stock solution do I need to add to water to make 1.5 total liters? Okay. So what? Let's go ahead and solve the math here. Multiply this together, divide by 16. Should be a nice small number. I get 0.00938 liters, which I could also write as 9.38 milliliters. That's how much stock solution I need. I'm going to take 9.38 milliliters of it, add it to my graduated cylinder, whatever else I'm measuring with. And then I'm just going to fill the rest with water. And I'm going to add enough water to get my desired amount of 1.5 liters. So 9.38 milliliters of just that stock solution, that really, really concentrated stuff. Fill the rest here with water until I get to 1.5 liters. And I will have made my desired solution. I'm just going to mix it up. My new solution has the same amount of moles of sulfuric acid that I started with. But I've just added extra water so that it's weaker overall. Its concentration, they're just more spread out. Okay. It's important to know how to prepare a dilution, which hopefully you'll have practice with, and we're going to practice it more going forward, but also know how to calculate that math with it. All right, so another concept check. A 0.5 molar solution of sodium chloride in an open beaker sits on a lab bench. So a little bit of salt water in an open beaker sitting on a lab bench. Which of the following would decrease the concentration of the salt solution? So if I want to decrease its concentration, that means I'm watering it down. I need to either add in some extra water somehow, or I need to remove the amount of salt somehow. If I wanted to increase the concentration, I'd have to do the opposite. Take out some water or add extra salt. In this case, I want to decrease it, so we need to do that. A says add water to the solution. If I added water to it, the volume is going to increase, but the number of moles stays the same. So that would decrease the concentration. Pour some of the solution down the sink drain. That's just going to reduce the total volume of it you have. But assuming it's mixed evenly, it's not going to change your concentration of your solution. Add more sodium chloride. If you add more salt, that's going to increase the concentration of the solution. Let the solution sit out in the open air for a couple of days. So if you do that, some of the water is going to evaporate away. So that's a way to reduce the amount of water, which will make it actually a little bit stronger, but we're looking for a decrease. At least 2 of the above would decrease the concentration. Nope. Only A did. B was neutral. C and D would both increase the concentration of it. So A is the answer. All right, enough with solutions. Let's go on to types of reactions. Synthesis, decomposition, single replacement, double replacement, combustion. Those are ones I cover a lot in honors chem. Some of these other ones maybe vary slightly, but like those are the ones we're going to talk about, but aren't really our focus for this year. Our focus are on these last 3: precipitation reactions, acid-base reactions, and oxidation reduction reactions. The last one, oxidation reduction, is so important that it's getting its own video after this one to talk about how to do those sorts of problems. And then acid and bases are so important, they actually get their full units. So like our unit 4, which we're going to do in like March, will be all about acids and bases. So today we're going to focus on, we're going to review those other types real quick, but they're not the most important things. So we have synthesis reactions here. When you combined 2 elements together to form a compound. So I have sodium and chlorine. I'm going to add them together to make sodium chloride. Magnesium and phosphorus, add them together. Sulfur, aluminum, add them together. So what you're starting with, what you should notice, you're starting with a simple element, and you're just going to combine it to make a compound. Okay. So when this happens, so the first one we had was sodium and chlorine. When you combine these, they're going to combine. You have NaCl. This is going to make an ionic bond, so we need their oxidation states. Sodium is 1 plus, chlorine is 1 minus. So when they make a compound, you're going to like swap those numbers. You're going to make those numbers cancel out. These are both just 1s, so it just makes NaCl. But on the next one here, I have magnesium. I have phosphorus. Okay, magnesium is Mg, oxidation state 2 plus. Phosphorus is P, oxidation state is 3 minus, I say like pretty confidently, but let's check. It's here, yeah, this column is 3 minus. Okay, I need those numbers to cancel out. The easiest way to do it is just to take this number 2, give it to phosphorus, this number 3, give it to magnesium. If you swap the numbers, it's like a shortcut to finding their greatest common factor. So they make Mg3, P2. And we don't write the negative sign because you couldn't have like a negative amount of something, right? That wouldn't make sense. Last one here, I have sulfur plus aluminum. Sulfur has a 2 minus charge. Aluminum has a 3 plus charge. You notice this time they're given to you backwards. It doesn't matter which one's written first, but when I make the compounds, you'll always see me write it the same way, where you put the positive charge first. The metal always goes first when you write a compound. The non-metal with the negative charge will always go second. You'll just notice that's how we write ionic compounds. compounds to keep it consistent. So even though it's written to me in this way, when I write it over here, I'm going to swap it around. I'm going to write Al first, and it gets the 2 from sulfur, and sulfur next, which gets the 3 plus from aluminum. Okay. There's nothing wrong with writing it the other way, but this is the way you'll always see it written to stay consistent. Okay. To save some time, I've already written out the answers to this one. Decomposition. Compounds break down into elements or smaller things. So this is the exact opposite. You start with a compound and you break into their components. Calcium sulfide. It's going to break into calcium and sulfur. Potassium chlorate. It's going to break into potassium chloride and oxygen. Sodium carbonate breaks into sodium oxide, carbon dioxide. So sometimes, like this top one is the simplest example. If you just have 2 elements, it's going to simply break into those 2 elements. These bottom 2 are polyatomic ions. Sometimes these break in unique ways. So you don't need to have these memorized or anything like this, but these are just some examples of different unique ways these things can break apart. A single replacement is a more active element replacing a less active element within a compound. If you check the very back of your notes, you have an activity series printed there. It's going to give you the order of activity of metals. Which metals are more reactive than other metals? The higher up you are on that chart, the more reactive you are. Reactive means you want to make compounds. Reactive things want to react with other things to make compounds. The bottom of this list, like things like gold at the very bottom of the list, are not very reactive. They're totally fine being by themselves. Just like we talk about the noble gases are non-reactive. They're fine being by themselves. Gold's kind of the same way. But something near the top of that list is very reactive. It's going to react with whatever it can. So number 1 here, active metals can replace less active metals. Lithium is very, very reactive. It likes to react with things. So it's actually going to replace the copper in this compound. And then also this works for some nonmetals, specifically the halogens, fluorine, chlorine, iodine, bromine, those. They can replace less active nonmetals. You also have a list of those 4 in order on your activity series as well. So just to do one of these examples real quick, I just want to show you number 1. Okay, I have my lithium, Li. This metal is just by itself, so it doesn't need any numbers or charges. It's just a pure metal at this point. And I'm going to add that to copper 2 chloride. Well, I need to write down the compound for that. Copper 2 chloride means this copper has a 2 plus charge, and it joins with chlorine, which has a 1 minus charge. Swap the numbers, that makes CuCl2. Okay. And I want to see what compound those make. Well, the lithium is more reactive than the copper because it's higher up on the activity series. So it's going to replace it. They're basically going to swap places in the products. Meaning copper is going to be left by itself. This copper needs no number or charge. It's just a pure metal, so it gets nothing. Plus Li and chlorine are going to join together. Lithium has a charge of plus. Chlorine has a charge of minus. So when these 2 mix together, they just have 1 of each. LiCl. Okay, then I just need to balance my equation. I have 2 chlorines over here, so I need a 2 over here, so I have 2 chlorines here, but now I have 2 lithiums, so I need a 2 over here. So that's my single replacement reaction between these 2. The reaction does occur because lithium is more reactive than copper. Then I just have to be careful when I make my ionic compounds to put the numbers, the subscripts in the right spots. I'll show you number 2 as well. Fluorine is F, but it's a diatomic molecule. It's a Brinkelhoff. These 7 atoms are diatomic, meaning when they're by themselves, they need a buddy. So F is F2. Plus aluminum chloride. It's made of aluminum and chlorine. Aluminum is 3 plus, chlorine's 1 minus. Swap the numbers to make AlCl3. Okay. So this time my fluorine is a nonmetal. It's going to try to swap with chlorine. but I can only do it if it's more reactive. So I'm going to consult my activity series. Is fluorine higher on the list than chlorine? Yes, it is. So we'll be able to make this reaction happen. The chlorine is going to be left by itself. Chlorine's also a Brinkelhoff one, so there's going to be 2 of them. Plus, the F and the Al are going to bond now. Al is 3 plus still. F is 1 minus. So I need to swap the numbers to get Al F3. To do a bit of balancing here to get all the numbers to work out, I have 2 chlorines and I have 3 over here. So to make those balance, I need to put a 2 here and a 3 here. So now I have 6 chlorines here and 6 chlorines here. Need my F's to balance out the same way. I have 3 here and 2 here. So I'll put a 3 here, 2 here, 6 fluorines, 6 fluorines, and I think it worked out. I have 2 aluminums, 2 aluminums. So everything's balanced after that. That's single replacement. All right. Third one here, or fourth one here, is precipitation reaction. This is another name for a double displacement, double replacement reaction we talked about. But this is a specific type in which a solid is formed and separates out from the solution. So in this, you're taking 2 liquids, usually they can be clear liquids, doesn't matter, adding them together, and they're making some sort of solid when those 2 things combine. And it's kind of weird to see that happen, because where did that solid come from? Well, it's coming from the chemical reaction occurring. When ionic compounds dissolve in water, the resulting solution contains the separated ions. Precipitate is just a fancy word for whatever solid is formed in a reaction. Okay, a couple different types of precipitates. The word soluble, meaning something, a solid that completely dissolves in a solution. It's giving the state of matter symbol AQ for aqueous. And if I have an insoluble thing, it's a solid that does not dissolve in a solution, and you give it an S for solid. So a precipitate that's made in a reaction will be a solid. Insoluble and only slightly soluble are often used interchangeably. So if something like sugar is like only partially dissolved in water, we just call it a solid. Okay, we need to be able to determine what things dissolve in what. So here are what they call, ironically, these simple rules for solubility. What sort of salts dissolve in water? Yeah, there's a lot here. All these weird exceptions. We're going to simplify those rules because memorization is not that important. These are more specific than we need to know. Our solubility rules we're going to use. To determine if something is soluble in water, we can use these simple rules. These rules are far from always true, but instead serve as a guideline as to what generally dissolves in water. If you have an ionic compound with K+, Na+, NO3-, or NH4+, so potassium, sodium, nitrate, or ammonium, those things in a salt will always be soluble. That's going to be our kind of steadfast rule we use. Now, there are exceptions, but that is scary. So we're just going to stick by those as things that are always soluble. Anything else, any other salts, if you have like barium chloride that doesn't contain one of those 4, we're going to assume it is a solid. But if it has any of these 4, we're going to assume it is soluble, meaning it's going to be aqueous. It'll dissolve. Okay. Other things will dissolve as well, like we're going to learn about acids and bases. Those always dissolve. But for salts, these are the 4 things that makes a salt soluble. We're going to apply that to our next type of reaction, a net ionic reaction. So we have a formula equation or a molecular equation. When you see that written in a problem, that just means like your normal chemical reaction, how you would normally write it. It gives the overall reaction stoichiometry, to a normal chemical reaction, but it doesn't necessarily tell you all the correct forms of reactants and products in the solution. Reactants and products generally are shown as compounds. Use solubility rules to determine which compounds are aqueous and which ones are solid. So here's an example at the bottom of a formula equation. Looks like a normal equation. But we're just going to add some state of matter symbols to that. based off of our solubility rules we just talked about. So I have AgNO3 contains NO3, so it is aqueous. AgNO3 will dissolve. Next one I have NaCl. NaCl is contains Na, contains sodium, so that will dissolve as well. So it's also AQ. AgCl contains none of those four we talked about. It doesn't have K or Na or NO3 or NH4. Therefore, according to our rules, it won't dissolve. It'll be a solid. So you're going to write a little S for AgCl. And then the last one, NaNO3, has Na and it has NO3. It has two of the things that will make it dissolve, so it definitely will dissolve. It's aqueous. Okay. We're going to use this to write a new type of reaction called the complete and net ionic equation. It represents all the ions as reactants and products that are strong electrolytes. An ionic equation shows which compounds are soluble, are going to turn into ions, and then which ones are insoluble. So it's a little bit more specific of a reaction, useful for solution stoichiometry. Here's our example. AgNO3, silver nitrate, is mixed with NaCl, sodium chloride. Write the complete ionic equation. All right. So I have AgNO3. Write that down, and I'm going to figure out what state of matter it is. So in parentheses, it has nitrate, so it is aqueous. Plus NaCl, it has sodium, so it is aqueous. Creates. All right, so this is going to be a double replacement reaction, meaning you're going to trade the places of everything. Ag is the metal over here. It's bonded to the non-metal NO3, so instead it's going to try to bond to the other non-metal Cl. So you're going to have AgCl. Both of these have a 1 plus charge, so you just get one of each, so you don't have to worry about any subscripts. But I need its state of matter. It doesn't have any of those four, like we talked about, so it's a solid. Plus Na is going to bond to the other non-metal, NO3. They both just have a 1 plus and 1 minus charge, so again, they just make NaNO3. This is definitely aqueous because it has two of the things that make it aqueous. That's my formula equation. That's our normal equation like we normally would write, but I want to write the complete ionic equation. I'm going to split apart all my strong electrolytes, all my aqueous things, into their ions. So like this first one, AgNO3 is going to split in Ag plus. The Ag plus is aqueous because it is dissolved in water. Plus NO3 minus, also aqueous. The second one is split into an Na plus, which is aqueous, plus a Cl minus, aqueous. All my aqueous things are going to split apart, but this solid is not. AgCl remains as a solid, so I don't split it apart. But this one is aqueous, so I have to. Na plus, aqueous, and then NO3 minus, aqueous as well. All right. No, that's a lot to write. That's my complete ionic equation. It's showing you how your things split apart. Excuse me. How your things split apart. Okay. Now we also have something called a net ionic equation. This includes only those solution components that actually change. Some of these things are just kind of dissolving in our liquid and not reacting with anything. They're not that important. This only shows things that actually react. If I go back to my problem here. On the left side, I have this Na plus aqueous. On the right side, I have the same thing, completely unchanged. Didn't react with anything. So I'm just going to cross it off. It's not important. Same thing here with this NO3. NO3 on both sides. Cross them off. This Ag plus, I don't have an identical Ag plus because this underwent a reaction and turned into AgCl. Same with this Cl. So I'm just going to rewrite this with only the things that actually react. Like that. That's called a net ionic equation. Only the things that are actually reacting with each other are included in the net ionic. Those ones we crossed off are called spectator ions. They're not actually participating in the reaction, they're just spectating it. So we just kind of cross them off. Na plus and NO3 minus we crossed off. Those are the spectator ions in the net ionic. A very common question you'll see on like the multiple choice section of the AP exam are like, which are the spectator ions in this reaction? So you kind of have to work out the complete ionic and cross off the ones that appear on both sides. All right. So here, we're going to put the whole thing together. We're going to write the correct formula equation, complete ionic and net ionic for the reaction between these two things. So I'm just going to write this down. Cobalt 2 chloride. Well, I need its chemical formula. Cobalt 2 chloride. Cobalt is CO. It has a 2 plus charge because that's what the 2 in Roman numerals means. Chloride is Cl minus. We'll just swap those numbers to make CO, Cl2. Now I need to decide on its state of matter. I don't see any of those 4 things that would make it aqueous, so I know it's solid. And that's going to mix with sodium hydroxide. Sodium is Na, charge plus. Hydroxide is a polyatomic ion, OH minus. They both just have a 1 charge, so they just make NaOH. It contains Na, so it is aqueous. So basically, if I think about this reaction, I'm taking this solid thing and adding it to some sodium hydroxide. And that's going to make, so I'm going to swap everything around. The cobalt is going to join up with the OH minus. The cobalt has a 2 plus charge, like we said over here. OH minus, that, swap the numbers to make CO, OH2, like that. Okay. This is going to be a solid because it doesn't contain any of the things that would make it aqueous. Plus, combine my other things, Na and Cl. Well, that just makes NaCl. That is aqueous because it contains sodium. All right, that's my formula equation. But I need to write my other 2 as well. I need to write my complete ionic and my net ionic. So all my solids will stay together, but all my aqueous things split apart. So I make COCl2, solid, plus this Na. Ooh, excuse me before I move on. I left out a step. When I have my formula equation, I need to make sure it's balanced. I have 2 chlorines here, only 1 chlorine here. The last time I kind of skipped that step because it was already balanced because everything was just 1. But let me balance this real quick. I need a 2 here, so I have 2 chlorines. But now I have 2 NAs, so I need to put a 2 here. 2 NAs, I have 2 OHs, 2 OHs, now everything's good. Okay, so I caught it just in time. Because when these 2 NaOH splits, they're going to make 2 sodiums with a plus charge, like that, plus 2 hydroxides with a minus charge, like that. On the right side here, this solid stays together, plus this aqueous one splits apart. 2 Na pluses, 2 Cl minuses. Like that is my full equation. This is what we call your complete ionic equation, just splitting everything apart into its components. But I want to write my net ionic equation by getting rid of any of my things that appear on both sides. And I spot 2 Na pluses over here, 2 Na pluses over here. So if I just recopy everything, that'll be my net ionic equation. And that'll be my full answer. All 3 of my equations written there. Formula, molecular equation, either one. Complete ionic, net ionic. All right. Last thing we want to do, I think, in this, solving stoichiometry problems for reactions in solutions. Step-by-step lists are nice. This whole thing is included in your notes. For me, that makes it really confusing. So I'm just going to move on to the example. I'm going to work through the example how I would do it. We're going to follow the step-by-step instructions, but I need to see the math first before I try to follow a list of instructions. Okay. Excuse me. Our example, it says when aqueous solutions of NaBr, PbNO3, are mixed, PbR2 precipitates. Well, that's giving you a little hint. If it says it precipitates, that means it is a solid. Calculate the mass of Pb2R2 formed. So I want to know, when I mix these two things together, how much of that solid do I make? I'm starting with, here are my ingredients, 1.25 liters of my PbNO3, 2 liters of 0.025 molar NaBr. There's a lot of information, a lot of numbers, a lot of symbols. It's confusing to look at. I'm going to organize my thoughts by starting at number 1 in those instructions. I'm just going to write down the reaction that's happening. So I have my NaBr. I'm going to write its state of matter. It is aqueous, because that's sodium. Plus PbNO3, 2. State of matter, also aqueous because it has the nitrate ion. They're mixed, and PbBr2 precipitates. Well, that'd be one of my two compounds when these two inner ones mix, but I'm also going to make NaNO3, aqueous, plus my PbBr2 like it says. That's a solid, which checks out. It precipitates. When I mix these, I just want to know how much of this I make. Okay. I have a molarity in a liter for NaBr and a molarity in a liter for PbNO3. What I need to do to make that equivalent is I'm going to turn both of those into moles. I have my balanced equation written out here. If I would like, let's start with this. I'm going to take this balanced equation and we're going to simplify it even further. Not all of this matters. I'm just going to write the complete ionic equation. Make sure it's balanced first. It's not. 2 here to balance out the nitrates. Oh, I see. Never mind. There's supposed to be a 2 here. 2 here to balance out the NaBrs. Fully balanced. All right. Going to split everything apart. 2 Na pluses plus 2 Br minuses plus Pb2 plus 2 nitrates gives you 2 Na pluses plus 2 NO3 minuses plus this solid at the end. Thank goodness, that's out of room. Okay. Let's get rid of the things that don't matter. My spectator ions, 2Na, 2NO3, 2Na, 2NO3. Only thing that matters is this reaction. Okay. Notice this reaction is fully balanced because it came from a fully balanced formula. 2 Br minuses plus Pb2 plus gives you PbBr2. Those are the only things that really matter. That's our actual reaction happening. So we've kind of simplified and gotten rid of a lot of that other stuff, which doesn't matter. We're just going to kind of start as that as our reaction. That's how the ionics are useful. All right, so I want to see how much Br minus I have, how much Pb2 plus I have. I'm going to use that to figure out how much PbBr2 I have. So I'm going to find out how many moles Br minus do I have, how many moles of Pb2 plus I have, and we'll go from there. So to get moles of Br minus, the information that gives me the problem that involves Br minus is 0.0250 molarity NaBr. And it says I have 2 liters of that. Now my information with Pb2 plus is 0.0500 molar PbNO3 2, and I have 1.25 liters of that. Okay, let's switch to my extra room here. Well, I'm going to use this. I'm going to find out how many moles of NaBr I have. Molarity is moles over liters. Molarity is 0.0250 moles over 2 liters times by 2, you get 0.05 moles of NaBr. That's NaBr. I need moles of Br minus. Okay? Well, fortunately, there's only 1 bromine in here, so 0.05 moles of NaBr makes 0.05 moles of Br minus. If there was a 2 or a 3 after the bromine, I'd have to multiply it by 2 or by 3. But because there's only 1 bromine in here, it just splits into 1 bromine anion. Repeat that over here. Molarity is moles per liter. Molarity is 0.05 moles over 1.25. Multiply this across, and I think that's 0.0625 moles of PbNO3 2. But I want to know how many just of the Pb2 pluses I have. Well, fortunately, again, there's only 1 Pb in each of these compounds, so that also means I have 0.0625 moles of Pb2 plus. If it was asking for this NO3, I have 2 of them, so I'd have had to times it by 2. But Pb2 plus, there's only 1 of them in my compound. So this is how many moles of each one I'm starting with. And what I want to find is my limiting reactant. Which one of these 2 reactants am I going to run out of first? Okay. At first glance, I have less Br minus. So that's the one I'm going to run out of first. But I do have to take into account this chemical equation up here. Every reaction uses 2 bromine minuses, 1 lead, 2 plus, to make one of these compounds. So actually, I use 2 of these every time. So if I'm thinking about how many reactions I can do, I actually have to divide it by 2. I can only do this many moles of reactions. This one, I only use 1 every time, so I only have to divide it by 1. Mole reactions. So either way I look at it, this is even now going to run out even faster than I thought before. So bromine is my limiting reactant. A lot of work we've done so far. We haven't found our answer. Let's not forget what we're looking for, which is just how much of this do we make. What we found is how much of this we start with, how much of this we start with. We figured out which one we're going to run out of first by seeing which ones we have less moles of. So what I'm going to do is just take my 0.05 moles of bromine. Now I'm going to do some stoichiometry to see how much PbBr2 I would make. So I'm going to convert this into moles. Br minus moles PbBr2, because that's what I'm looking for. Well, 1 of these, because the coefficient of the reaction is 1, 2 of these. Okay, and then I'm out of room, but 1 mole of this, PbBr2. I need to find how many grams that is. So I'm going to go to the periodic table, add Pb and Br2. It's really big, 367. Now if I multiply 0.05 times 367, divide by 2, I get an answer. That's my answer. Ton of work. That's solution stoichiometry. Okay. This would be considered a very hard problem on the AP exam. There's a lot going on here. We will have lots of these to practice. Okay. Okay. Oh, actual last thing. Just going to briefly talk about neutralizing acids and bases. An acid-base reaction is also known as a neutralization reaction. Once the exact amount of base is added to react with an acid in solution, the acid is said to be neutralized. What this means, if I have 10 moles of strong acid, to neutralize that, I need 10 moles of strong base. If I add 10 moles of strong base, I've now completely canceled out everything. I'm left with just like water. It's completely neutral. Couple of vocab words with titrations. Titration is a method that's very important. We're going to do a lot after the break. We're going to talk about the math involved with titrations because it's always on the AP exam. And then we're going to actually do some of these in the class. So over here on the right, you have a burette, which is like a fancy tool for measuring volume. And it has what's called a stopcock, which is a tiny little like lever you can turn to like make liquid come out of your burette. You're gonna have some acid of unknown concentration at the bottom, and then you have a base so that you know its concentration. And basically, you're just gonna keep adding until your acid is completely neutralized. When your acid is completely neutralized, the moles of base you use to neutralize it is equal to the moles of acid you originally had in your solution. Okay. We'll talk about this vocabulary kind of together later. Okay. Last question we're going to have for today. What volume of 0.1 molar HCl is required in order to neutralize 25 milliliters of 0.350 molar NaOH? Okay. So to neutralize moles of your acid must equal moles of your base. HCl, I don't know how much of it I need, but I'm going to start with NaOH. Molarity is moles over liter. I have 0.350 molar. I have 25 milliliters, which is 0.025 liters. I'm going to multiply that. That equals 0.00875 moles of NaOH. That's how many moles of NaOH I had. If my solution was completely neutralized, that's also equal to the moles of HCl. Okay. Well, I want to know what volume of HCl I need. I now know how many moles I have, and I know its concentration from the problem. 0.10 molar. I have 0.00875 moles of it, because it's equal to the moles of NaOH, over liters. Solve 0.100 liters equals this number. Divide by 0.1, which is multiplied by 10. I need 0.0875 liters or 87.5 milliliters to neutralize. Okay. Next time, we're going to pick up with the redox reactions, okay? So the rest of the notes here, we're going to do in the next video. Thank you.